Good morning and welcome to this next lecture on sound and structural vibration. So today I am going to summarize the entire sound in a structural acoustic waveguide problem. Okay, so structural acoustic waveguide. So this was the problem. So we had a waveguide with a top rigid plate and a bottom flexing plate with an acoustic fluid. Okay. Now I will just summarize. Okay. One is the coupled curves cannot cross uncoupled curves. Except at certain critical points. 2. The structural wave number below coincidence, okay, below coincidence, below omega equal to 1, okay, sees the fluid as inertia, hence wave slows down, which means the lambda x will drop, which means kx will go up. That is what happens. Okay. Next, the structural wave number above coincidence, above omega equal to 1, sees the fluid as stiffness, and inertia alternatingly. Okay. And crossing the pressure release point, the pressure release critical point. Where briefly structure and fluid are decoupled. Okay. Next, the coupled acoustic wave number, coupled acoustic plane wave, okay, above omega equal to 1, sees structure as stiffness. which means at infinite stiffness, let's say infinite stiffness, the uncoupled plane wave is obtained. With finite stiffness, of the plate, the wave slows down that means lambda x goes down and therefore kx goes up. Okay. Below coupled acoustic plane wave below omega equal to 1, okay, sees structure as inertia. Okay. At infinite inertia, the uncoupled plane wave is obtained. Okay, coupled plane wave is obtained, and for finite values lambda x has to go up, okay, reduction of inertia, and therefore kx will start going down. Okay, I think point number 6, the coupled rigid duct cut-ons start below uncoupled curves as they approach the uncoupled flexure, they smoothly transition to coupled flexure which passes through the pressure release point, pressure release critical point, and follows next rigid duct cut on. Okay. And finally as epsilon goes up, okay, the rigid ducts, the, let's say, coupled rigid duct cut-ons start shifting and approach the pressure release cut-ons, the uncoupled pressure release cut-ons. Okay, they are better identified. They are now better identified as the coupled pressure release cut-ons. Pressure release cut-ons. So that's the story of the structural acoustic waveguide. Okay. We are now going to start looking at the next problem, which is a cavity, okay, a cavity of acoustic fluid interacting with a panel. Okay. So this is a flat panel which can vibrate, and this is a cavity with volume V having an acoustic fluid. So now we you can note the progression. We did an infinite domain problem, an infinite plate, an infinite half space. Okay. Then we looked at a structural acoustic waveguide where in one dimension it was infinite, in the other dimension it was finite. Now this is a finite realistic system where you have a cavity interacting with a vibrating panel. Okay. So each will influence the other, that is the idea. Now with regard to this, I will follow a particular journal paper. It is by the following authors: S. M. Kim and M. J. Brennan. It is a journal of sound and vibration, sound and vibration paper. Year is 1999. The volume is 223 part 1, pages 97 to 113. Okay. And it starts with it has a long title, so it starts with this title. Let me put it. a compact matrix formulation, etc., formulation with mobility, etc., etc., and structural acoustic system. Okay, so I will follow this particular document almost closely with notation, etc. Okay, now to begin with, suppose I have a system like this. Okay, and I apply, so this is a structure. Okay, let me see what this is. This is a structure. Okay, and there is acoustic fluid inside. So now suppose I apply a force, okay, at some location. These are very general ideas, so nothing is very fixed. Okay, so these are schematics. So I apply a force, okay, to the structure. So what happens is that force will be partly taken up by the structure, which I say Fs of R, okay, and partly by the fluid, acoustic fluid, Fa of R. Okay. Now the structure deforms. The structure deforms through its impedance, which I call Z structure of R into U of R. Okay. Now this is a common velocity junction. Okay, it's a common velocity junction. And therefore the force will split and the velocity will be common. Okay, so that means UR is common to the structure and the fluid. So the force taken up by the fluid is given by the fluid acoustical impedance, okay, into the same velocity. Okay. Now if I use this equation, let's call it maybe 1, okay, and I divide both sides by the common velocity. So divided by the common velocity plus F A by the common velocity, that is equal to the total force by the common velocity. Okay. So now what happens over here? So this is equivalent to saying Z S of R plus Z acoustical impedance of R, okay, into U of R is equal to F of R. Okay, or alternatively UR now is given by Ys of R divided by 1 plus Ys of R ZCA of R, okay, into F of R. Okay. where Ys, let's say where Ys is equal to 1 over Zs. Okay, Ys is called mobility, structural mobility, and Zs is called structural impedance, and it has force over velocity units. So Zs has force over velocity units, which means it has mechanical impedance units, Okay. Now the applied force gives rise to a pressure also. Okay, so that pressure in the fluid, okay, is given by the force taken up by the fluid, which is R, by some area, some notional area. Okay, so this becomes equal to the total force minus what is taken up by the structure divided by the area. Okay, and this is equal to the force minus Z structure impedance UR over S. Okay, now rewriting F of R minus Zs of R U of R by S is equal to F of R by S minus Zs of R by S into what we found earlier, mobility, structural mobility, 1 plus Ys, Z acoustic impedance, F of R. Okay, I should just mention that typically when we say acoustic impedance, it's pressure over velocity. Okay, so I am kind of using a sort of incorrect language. This is acoustical impedance in the units of mechanical impedance. Okay, mechanical impedance related to acoustics. Okay, so then what happens to this? This becomes finally equal to S, not this. Okay, the derivation becomes equal to, so P of R becomes equal to S Ys of R. Okay, and here comes another idea, Z A of R divided by 1 plus Z A of R and one more Ycs of R into F of R. So what is ZCA? ZCA divided by S square is ZA. Okay, so ZCA is acoustical impedance. ZCA is acoustical impedance in mechanical units. Okay, in mechanical impedance units. force over velocity units. Okay. So ZCA divided by a single S is actually the acoustic impedance, which is pressure over velocity, which is pressure by velocity. Then ZCA over S square is what we call specific acoustic impedance. Specific acoustic impedance. Acoustic impedance. Force over area square units. Okay. So that's what ZA is. So ZA, the acoustical part, is in proper acoustical units. Similarly, let me write here YCS. What is YCS? Okay, that is S square times YS. Okay, or S square over ZS. Okay, so ZS is mechanical units. So ZS over S square is like your specific acoustic impedance related to structure. So YCS is inverse of that. Okay. So ZS and YS are proper structural mechanical impedance units, whereas ZA is the appropriate specific acoustic impedance. Okay. So for a structural force, applied, we have found the velocity, common velocity, and the pressure inside the fluid. We have done that so far. Okay. Now, if you see what happens if there is a volume velocity input, volume velocity input. Okay. If I draw the picture again, so I have this domain, let me keep an opening, I applied a force, so this direction is kind of positive, you can see. So there is a velocity in this direction. Okay. So this is taken up by F acoustic and F structure, and inside there is a pressure. Okay. Now, if a volume velocity is given, okay, effectively here a volume velocity is given. Okay. So that will also generate a velocity, and that will also generate a pressure. Okay. Now what happens? The Q also gets divided by a compressive part related to acoustics and a deformation part that the structure takes up. Okay. So the QA part gives rise to pressure, and the QS part, okay, gives rise to velocity. So how does that happen? So one thing you should note here is that a positive force here generates a velocity in one direction that causes an increase in pressure. Okay, you can see from the directions and so forth. Whereas if a volume velocity is given and that causes a rise in pressure, that generates a velocity, it is going to be opposed to what the force generates. That is actually the crux. There is a sign convention we have to observe. That's the crux of the matter over here. Okay. So now let's see. My Q minus Q of S is equal to QA. Okay. And QS QS is going to be related to the pressure. Okay. QS is related to the positive pressure. Okay, that's the pressure that is going to take that deformation. Okay, so that's S square divided by ZS. You see where the notations come in. Okay, this is equal to S square into YS. Okay, the pressure that got generated deforms the structure and to this extent. Okay, deforms the structure, that is this QS. Okay. Now if I have the total input volume velocity over pressure, okay, that is equal to QA by P. Okay, this is in proper acoustical units. Okay, so this will be this will be YA. Okay, plus I have Q of S by P. So that is going to be equal to YA plus S square YS. Okay. So we have given the notation before, this is 1 over ZA plus this is YCS. Okay, S square YS is YCS. Okay, so what happens to now my P here? P is equal to ZA by 1 plus ZA YCS into Q. Okay. You can see here that if YCS is 0, if YCS is 0, that means the structure is infinitely stiff, then PA and Q are directly related through ZA. Okay. Now here is the with QS. Okay, with QS, the way QS deforms due to the pressure, we have to bring in a sign over here because that velocity is in the opposite direction. So this becomes equal to minus S square YS times a P divided by S. Okay, from here. Okay, so that now is equal to minus S into YS into ZA by 1 plus ZA into YCS into Q. Okay, this pressure found from this. Okay, so finally what do we have? We have pressure and velocity due to a force applied to the structure due to a volume velocity put into the structure we have. Okay, so my pressure is equal to ZA Q plus S YS of F by 1 plus ZAYCS, and U is equal to YS of F minus SZAQ over 1 plus YSZCA. I'll stop this lecture here. We'll continue next time. Thanks.